which is not bad for a microcontroller. But I expect that you aren't going to even bother to try and have them run that fast, because the filtering operations are fairly lightweight, actually. I'm going to ask you to do. Any questions about the stack machine? Started describing it. We'll describe it a little bit more today, and then start talking about the compiler a little bit. And I'm not going to write out the code for the whole stack machine because it's bulky, but I do want to talk a little bit about the interface to the CPU, and emphasize that this is a design that is GPL'd from Hiroshima University. So the interface to the microcontroller is very simple. Memory is referenced from inside the CPU, so the only thing that is brought out from the CPU to the outside world is a clock line, a reset line, and a run stop for debugging, so you can freeze the CPU, and 4 I/O ports. So the interface, the module as defined, if I can find the module as defined, is and I just called this mini CPU. That was the name that the researchers at Hiroshima used for it. But it needs a better name, so if somebody can think up a better name, go for it. And input parameters, or the I/O parameters, are clock, reset, run, in 0, in 1, in 2, in 3, out 0, out 1, out 2, and out 3. That's straightforward. Each of the input and output ports are 18 bits. And so on. Output 18 bits. Out 0, and so forth. And of course, clock, reset, and run are inputs. There's no reason why you can't hack on this CPU to bring any other signal out that you want for debugging. Address bus, program counter, whatever you can put out through the interface. The code is fairly compact. It's moderately easy to understand, and feel free to hack on it. One reason I went for 4 I/O ports was that I'm not sure of this. You'll have to make this design decision in the next lab, in Lab 3, that it would be useful to use a small processor like this for simulating the drum head that you're going to have to do in Lab 3, where a given node has 4 nearest neighbors, and hence 4 I/O ports is about the right number. It's a single cycle CPU, calculates a new result on every clock cycle. The maximum addressable memory is 4,096 words, 18-bit words. Why 18 bits? It's the natural width of the M4K blocks. By setting a parameter inside the memory module, or by passing a parameter to the memory module, you can lower the number of words from 4,096 down to a lower number, assuming that your code will fit in a smaller memory area. The CPU will execute out of a single M4K block. So it scales relatively well. Scales relatively well down to small sizes. There's a two-ported RAM that the CPU uses internally. And I'm writing out just the interface for a very limited reason, and that is that inside this module is where you specify the name of the file that has the code you want to load into memory. Because you're going to have to use a compiler to make code, and then you want to make sure that the code ends up in executable memory. There's a clock, of course, a load signal, an address 1, an address 2, a data 1, a Q1, which is an output, and a Q2. And parameters which are specified, which you can also pass in. You can override local parameters. Data width is going to be set to 18. Probably shouldn't mess with that, unless you're ready to do some serious recoding. The address width must be 12 in order to get 4,096 words. But that you can reduce if you want to go for smaller memories. And the number of words and really there's only one line I want to write out here, because this has the synthesis directive that you need on it. And that is the line that actually defines the memory, which is going to be a memory of d width minus 1 down to 0 of memory words minus 1 down to 0. And then the magic phrase that tells the compiler what the synthesizer what code to include is /* synthesis. So it's a Verilog comment, but the synthesizer software notices it. RAM init file equals whatever your file name is, test1.mif, quote, star slash, and then the semicolon. Turns out, it looks like a comment, but if you put it after the semicolon, the synthesizer doesn't find it. That took me a while to figure out. That wasn't documented. So, you're probably thinking to yourself, oh no, every time we recompile a program to run on this CPU, now we're going to have to resynthesize the whole project. Were you thinking that? Hadn't gotten there yet. And as you all know by now, the full synthesis is kind of slow. And so you don't want to do that more than you have to. But there's a shortcut. So, I mean, in general, no matter what you do, of course, you're going to use a text editor to write source. And you can use any text editor you want. I know there's some people in here who are Emacs geeks. I just use WordPad. Then you're going to use the MATLAB program to compile it. And if you change this name, if you change the name of the file, then you have to run Quartus 2 and recompile the project. But if you just change the contents of the file without changing the name, say if you're doing an edit, compile, test cycle, then in Quartus 2 you can say, you can go to the processing menu and choose the item update mem init. Huh, handy. And that takes about 4 seconds. And then you say processing, menu item processing, start assembler, and that takes another 4 seconds or so. And with those 2 steps, then you will have incorporated the new source code, or the new object code, the new memory image file, into the RAM. Any questions? There's a page which describes the small CPU, the stacked CPU, and you're going to want to read that real soon. And maybe load up one of the examples and try out the example. And then maybe there'll be some questions. Oh, maybe I ought to write out a little bit of source code here. That'd be a good idea. I better talk about the compiler. So, a program consists of the usual names, operators, and structuring elements. I didn't write a C preprocessor or anything like a C preprocessor for it, but but you can define constants by the keyword constant, which is then followed by a name and value pair. You can define variables. So essentially it's declaring. There's one data type, and so this is a declaration. The only data type is integer, 18-bit integer. And so you can have a name or a name plus a size. And if you put a size here, then it becomes an array. So you've declared a single variable, or you've declared an array variable. There's no actual array bounds checking done or anything like that. So if you don't declare this as a variable, it'll just stomp through memory using whatever indices you want for whatever you want. But this is how you declare a variable of the size of a variable. Program execution starts at a symbol called main. That's at least vaguely C-like. Actually, it's main colon. And using the name of a constant or a variable, puts its value on the stack. That's all it does. Prepending an equals to the name of a variable takes what's on the stack and stores it in that memory address. So that's a store operator. So if you had well, we'll do an example in a minute. If you use the form variable, do it this way, name one, name two, with square brackets, name two is used main. Main two is used as an index into name one. Square brackets, just like C, except the parser is really stupid. And so you can't put spaces any place in this string or that string. Equal name one, main two, uses main two as an index into name one and stores the value at the top of the stack into that location. The available stack operators is, you can look up, but it includes add, subtract, shift left, shift right, bit and, bit or, equals, not equal, greater than, less than, not, drop, and over. Not, what's drop? I guess I ought to talk about a couple of these stack things that you probably never heard of. If you use the operator dupe, it takes the top of the stack and makes a copy of it. So top goes to top on the stack. If you use drop, next and top goes to next on the stack. If you do an over, then next and top go to next, top, next on the stack. So there's a whole bunch of stack operators you can use. Input and output are defined by a constant typically from the name of a list of name of constants, but it can be an integer. There are two kinds of functions. There are inline functions, which do exactly what you'd think. It puts the code inline wherever you use the name of the function. This is used for efficiency, where you have a short function. You don't want to have to do all of the pushing and popping necessary to do a function linkage. And then there are called functions, which use the stack as a parameter list use stack for parameters and use a program counter linkage for the return value. An entry point of a called function entry point of a called function is exactly like main, but with a function name. And the end of a function is indicated by a return. Body of function, return. Values that are submitted to the function are on the stack. Return values are on the stack. There is no separate mechanism for handling function values because there doesn't need to be. So probably we should do an example. Oh yes, there is the assembler is inline. Yeah. No interrupts on the CPU unless you write it. You can write an interrupt handler. I thought about having you do that as an exercise, but I couldn't quite get together what the interrupt should do. I'd have to have you write, say, a timer module or do some interesting I/O interrupt stuff, and I decided I wouldn't do that. Maybe next year. But an interrupt handler requires an extension to the basic CPU state machine because it has to exist between instruction calls, right? Between instruction states, and so it requires an extension to the state machine. Assembler is completely embedded in the compiler, and the way you specify an assembler command is opcode period operand. So for instance, let's say that you wanted to write a command swap which takes the top of stack and the next to top of stack and converts it to top next. So it takes the two values on the top of the stack and flips it. I did not do an assembly language instruction for that, although it's useful. So instead what you do is you say, I want an inline called swap. So the syntax is inline swap. And it was so useful to have just a few unnamed memory locations to use. I left 4 memory locations that are not available for the compiler to use, but the assembler can use. And you can change that number easily if you need more reserve space. But its address is 4, 5, 6, and 7 in memory. So we can do a pop dot 4, means take the top of the stack and put it in memory location 4. Pop 5, that takes the next value and puts it in 5. Push 4 dot 4, push dot 5, and end inline. So that's now a inline function, and if you later use the word swap, use the token swap, then these 4 assembler commands will be inserted into your code. So all the compiler does is to generate code to initialize a return stack, and then it jumps to main. Return stack is in high memory. 04096. Stack grows down. There's a max stack size, and below that are variables. So let's do an example in this strange language. Any questions? I found writing this very entertaining. I hope it's entertaining to use too. So what this program does is just do a bunch of manipulations of the LEDs. So it allows you to flip switches and turn on LEDs on and off, and so it runs on the board without any peripherals to use. So it's a nice test program. It does assume, of course, that certain input and output ports are connected to certain chunks of hardware outside. So in this case, one of the input ports is going to be connected to the red LEDs. In fact, we'll start by writing the constant list here. We're going to have a constant called red LED, which is going to be hooked to I/O port 3. We're going to have green LEDs, which are hooked to port 2. We're going to define the word forever to be a 1. That's going to be useful for an endless while loop. Because like all embedded programs, there's always an endless loop, right? There's nothing to exit to. And so there has to be an endless loop. And then we're going to need some masks and some other constants. So we're going to define a key 3 mask to be 8. That's the binary value of the third push button. And a key 2 mask to be 4. And the keys are going to be on all input on port 1. And key mask 15 will be used to limit the push buttons to 4 push buttons, because after all, it's an 18-bit port, and I don't want to be doing comparisons above the 4 bits I know are valid, which are the 4 push buttons. Variable test, counter 1 and counter 2. And so these are all one-word variables. We're going to do an inline 1 add and inline. What this says is, take whatever value is on the stack, leave it there, push a 1 on the stack, and then add what was ever on the stack before to the 1, and leave it on the stack. So that just increments the value on the stack. It's postfix notation, so you have to add. So if you want to add 2 numbers, you have to say 3, 1, add. Standard postfix notation. You familiar with postfix notation? Some CS people probably are. Postfix is often more regular than infix. This would be infix. And there's going to be a function, eval key. We're not going to write that now, we're just declaring the function name. Because again, the parser is really stupid. Then we can write main. First thing we're going to do is reset the green LEDs. So we're going to say 0 out green LEDs. And then 0 out. No, actually we're going to zero a counter. So we're going to do 0 equals counter 1. No space. Equals counter 1. This 0 pushes a 0 on the stack and outputs it to the green LEDs. So it pops the stack into the output register. Again, we write a 0 to the stack and then store it into the counter 1 variable. Then we're going to do a while forever. Forever always evaluates to 1. It's a constant that always evaluates to 1. So it leaves a 1 on the stack for the do defined, which says as long as there's a 1 on the stack, when we hit this token, we will then do whatever is in the body of the loop. Counter 1. So we're going to load counter 1 back onto the stack, increment it, dupe it. So now there are 2 copies of the counter on the stack. Output 1 copy to the red LEDs. And save the other one. back to counter 1. So this puts a number on the stack, this increments it, this makes a copy, so there's 2 versions on the stack. This takes one of the copies, outputs it, takes the other copy, and puts it back into counter 1.
So the out operation will actually pop the top of the stack, right?
These pop the stack into the yes. Operations always pop the stack.
What is the first statement to zero out green LEDs? It puts a 0 and then pops the 0 and assigns it to the LEDs? How does it work?
Yes. It pushes a 0 on the stack, and then out pops the stack into the output register. Now we need to slow this down a little bit. I couldn't see the counter count because the clock rate was too high. So I made an inner loop. So we're gonna preload counter 2 with the value 1, and then say while counter 2 0 not equal do. So that takes the value of counter 2, puts it on the stack, puts a 0 on the stack, pushes a 0 on the stack, compares the top 2 values on the stack. If they're not equal, it does the body. It actually, what it does is it returns a 1 on the stack if they're not equal. It returns a 0 on the stack if they are equal. If it is not equal, then there's a 1 on the stack. The do picks up the 1, and we do a counter 2 increment equal counter 2. End while. This syntax makes sense? It's clear how the syntax works? I'm getting a lot of very kind of abstract expressions here back.
Where are the variables actually stored when you declare?
RAM. And then decided to, well, by way of testing if then else and fiddling with I/O, I made a little block that tested various push buttons. If key mask key 3 mask, if key 3 mask eval key. Eval key is a function which we haven't written yet, but it returns the value of the push buttons. So eval key will take this key mask in and return, actually it returns a binary, a 0 or a 1, depending on whether the pushed buttons match the key mask or not. So if we have a match, then we're just going to push a pattern out, push immediate, pattern 2. I think pattern 2 is another constant. I forgot to write it. Push immediate pattern 2, and then out dot green LEDs. This is just by way of showing that I can embed assembler directly into the compiler, and that push immediate dot pattern 2 picks up the value of the constant, uses it as a parameter for push immediate, which takes this value and pushes it immediately onto the stack, and then out is an assembler command that takes the value on the stack and outputs it to the LEDs. So this is the assembler version of loading a pattern, of loading a variable and outputting a variable to. Else, we're going to do this is a slightly odd operation that I just did for testing. Push PC dot. Push PC takes the program counter and pushes it onto the data stack. The dot's necessary because it's an assembler command with no parameters. And then we're going to output that to the green LEDs. And then end if. And then end while. This end while is the end of this one. So at this point, the only thing we need then is the function call, eval key colon, that's the entry point for the function. We're going to do an in of keys, which takes an 18-bit value from the input whose constant is keys, which was what, 1, I think. And the push buttons are all inverted logic, and I don't like to think in inverted logic, so the first thing I did was a B naught. That takes whatever is on the top of stack and inverts it bit by bit, bitwise not. Then we're going to do a key mask and bit and. That limits the total range of possible outputs to the first 4 bits, because key mask was value 15. And then do an equal. Oh, wait a minute. What's that equal to? What? It's equal to key mask was on the stack when we did the eval key. So key mask is an input parameter to eval key, which is sitting on the stack. We come into here, it's still on the stack. You do these 2 operations. The equal says take the result of these 4 operators and compare it to the next value on the stack, which is key mask, and return a binary 1 or 0. The output of functions is on the stack by default. So that's where this is going, because equal leaves a 1 or a 0 on the stack, which is then used by the mainline program. So a couple of you are smiling, and a couple of you look nauseated. Is this a familiar style? Yes? Some of you have seen this kind of style of programming. But it's easy to learn because it's very, very regular. There are no exceptions. For instance, in normal arithmetic, you use infix for operators like plus, but you use prefix for operators like sign. and you use postfix for other operators. These are all postfix operations. Everything's postfix. On the stack web page, there is a list of the operators you can use on the stack. It's basically integer arithmetic and logic, plus a few weird stack operations like dupe and drop, which just make the efficiency better. So what I'm going to ask you to do then in Lab 2 is I'm going to ask you to write a program that runs on two separate processors simultaneously that implements a infinite impulse response digital filter. So how many people can define the difference between infinite impulse response and finite impulse response filters? Hold up a hand. One. That's it, huh? Okay, we'll talk about filtering next. But you can get started over the weekend by taking the example stack machines that are on the stack page, download them, program them up, and start hacking on the code. Modify the code. Get the compiler running in MATLAB. And don't modify the compiler unless you feel really brave. But if you do, that's okay too. I mean, you can probably write a better one than I can. But download the source code. Start hacking on the source code. Fiddle with it. Get a feel for what you can do and can't do in a stack language. I did some elementary error detection. The system detects undefined tokens. It detects poorly nested if-then-else and while loops. And it detects a few other structural things. But I can't say it's a very robust error detection. It's easy to break the error detection system. Keep your code simple. And actually for an infinite impulse response filter program, the code should be extremely simple. I doubt if you'll even have to have a branch statement. Well, you might have to have, you will have to have at least a loop and a detection of some sort of synchrony. Because you're going to find that this CPU runs so fast that you're going to have to wait quite a while between samples. The audio samples are going to come in at 48 kilohertz. Your calculations are going to be done in less than a microsecond probably, maybe 2 microseconds. That means you have to wait for about 22 microseconds or 20 microseconds until the next sample is ready, which means you're going to have to figure out some way of detecting when the next sample is ready. And that's obviously going to be some sort of interlock, which means some sort of conditional, since there's no interrupts on the CPU. Unless, of course, you want to write an interrupt handler in hardware, which would be fun. Any questions? Read over the weekend. Do a lot of reading over the weekend about stack machine. Look at the, don't necessarily look at the compiler, but look at the source code. Start playing with it. 2 weeks is not a long time.